Okay, in this video, we want to look at some formulas for right, left, and midpoint approximations. So again, we want to approximate the area under the curve y equals f of x on the closed bounded interval from a to b. And each one of those approximations used a uniform partition. So the width of all of our rectangles that we will use to approximate this area, the widths are all the same, right? So a uniform partition. So if y is equal to f of x on a to b, and we let delta x be b minus a over n, so remember this is the width of all of our rectangles, then here is a formula for r sub n, right? It's delta x, remember we factored out, so normally it was the height times the width, but there's no I in delta x, so I can factor it out. So I've got the width, and then I want to add up all of the heights of the rectangles. So in this case, the right endpoint approximation, we go from I equals 1 to n, and the heights are given by f of a plus I times delta x. For the left endpoint approximations, instead of starting at 1 and stopping at n, we will start at 0 and stop at n minus 1. And if you want, you can reshift this thing around. So instead of starting at 0 and stopping at n minus 1, right, you can add 1 to both of these things, but then subtract 1 from the I in the sum end, right? So instead of going from 0 to n minus 1, we go from I equals 1 to n, but change this I to I minus 1, right? And then the midpoint approximation is given by this thing. So let's take a look at a proof of a couple of these things. Maybe not a formal proof, but we'll draw a picture to see exactly why we get each of these expressions. Okay, let's look at why we get the expression that we do for the right endpoint approximation using n rectangles. So for the right endpoint approximation using n rectangles, we are trying to approximate the area under the curve f of x on the interval from a to b. So again, the slice part is really the most important part. So we take our interval from a to b and cut it up into n equal parts. So my delta x, as always, it's b minus a divided by the number of rectangles. In this case, it's going to be n. So once I get the width, I just start at the left endpoint and keep adding the width to itself over and over again until I reach b. So we start at a, and then the first subinterval is going to stop at a plus delta x, right? And then I add delta x to this thing, and I get a plus 2 delta x. And the next one is going to be a plus 3 delta x, blah, blah, blah. So using I as the general expression, right, the general counter, right, the ith subinterval will start at a plus I minus 1 times delta x and stop at a plus I times delta x. So right here is the general ith subinterval, right? Here's the first endpoint, and here's the right endpoint. And then you keep doing this until you reach b. Okay, so now let's look at our counter I equals 1, right, starting at 1, 2, the general I minus 1, the general I, blah, 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 up to I equals n. So in the first subinterval, right, we are using the right endpoint approximation. So the sample point that I will use to get the height is x1 star is equal to a plus delta x. So a plus 1 times delta x. On the second subinterval, right, on the second subinterval, the way we will obtain the height is to plug in the right endpoint of the second subinterval. The right endpoint is a plus 2 delta x. We will take that thing and plug it into the function to get the height of the second rectangle. Okay, so when I get to the ith subinterval, right, that's this thing, its right endpoint is a plus I times delta x. And so I'm using the right endpoint. We don't need those. I'm using the right endpoint to obtain the height of the ith rectangle, or the right endpoint here, which is a plus I delta x. So you just take this thing, plug it into the function. This is going to be the height of the ith rectangle, so on and so forth. So now, in general, the area of the ith rectangle then, using the right endpoint, is f of a plus I delta x times delta x. And so now we just want to add all these things up. Right, so Rn then is equal to the following. Right, I'm adding up all of these things, and I've got a 1, a 2, a 3, blah, 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 and I stopping at n. So I'm starting at 1 and stopping at n. And so here I've got the sum I goes from 1 up to n, f of a plus I delta x times delta x. But now delta x doesn't have an I in it, right? So that thing is constant with respect to our counter. So I can just take this and write it out front. All right, so here's our expression for the approximation for the area under the curve y equals f of x on the interval from a to b using n rectangles. Okay. Okay, so for the midpoint approximation, once again, right, we want to take our interval and break it up into n equal parts. Again, delta x is always b minus a over n. So the first subinterval goes from a to a plus delta x. The second subinterval goes from a plus delta x to a plus 2 delta x. The ith subinterval, so the general expression, goes from a plus I minus 1 delta x to a plus I delta x, blah, blah, blah. So what we want to do is to find the midpoint, right, the general midpoint of this ith subinterval. And how do you do that? Well, I'll add up the two ends and then divide by 2. So I've got a plus I minus 1 delta x plus a plus I delta x all over 2. So here I'm going to get 2 a's. And then here I get an I delta x and then another I delta x. So I've got 2I delta x. And then I'm going to subtract 1 delta x and then divide all that by 2. So everything in the top here except the last part, right, these first two things are divisible by 2. So I just get a and then plus I delta x and then subtract delta x over 2. So now here's my sample point. And now once I have my sample point, that's going to tell me that the height of each rectangle, right, the height of each rectangle is going to be f of xi star, or f of this thing. Right, so to get an approximation, I want to add up all the areas. The height is going to be f of this xi star, so a plus I delta x minus delta x over 2 times delta x. And now you can just factor out a delta x because it doesn't have an I in it, right? It's constant. And so here I'm just going to get delta x, the sum I goes from 1 up to n, f of a plus I delta x minus delta x over 2. Right, so here's our expression for the midpoint approximation to the area under the curve f on the interval from a to b using n rectangles. And so now the last thing that we need to do in order to get the exact answer is just to let the number of rectangles go to infinity. Before we do that, though, let's look at a few examples just using this formula. let's compute R4 and M4. So we want to approximate the area under f of x equals sine of x on the interval from 0 to pi. And this is just one arc of the sine function, right, going from 0 to pi. So we want the area in of this region here. So to find R4 and M4, we will always need delta x, so that should be step number 1. So b minus a over 4 in this case, so that's going to be pi over 4, so there's my delta x. And now we know that R4 is given by delta x, the sum starting at 1 and stopping at 4 of f of a plus I delta x. So in this case, our f is sine, right? A is 0, and so I get 0 plus I times pi over 4. So here I just got sine of I pi over 4. So if we work this thing out, then we'll be good to go. So again, pi over 4, we'll write that on the outside. And now the first thing I get is the sine of 1 pi over 4. That's sine of pi over 4. And then the sine of 2 pi over 4, or the sine of pi over 2, plus the sine of 3 pi over 4, plus the sine of 4 pi over 4. So you can work all this out with a calculator, and when you do, you get 1.8961. And actually, I think the exact answer is like pi over 4 times, right? It's pi over 4 times root 2 and then plus 1. So you can get this answer by hand, or you can get this answer using a calculator. Okay, so that would be a good final answer for the right endpoint approximation using 4 rectangles. Coincidentally, the actual area is going to be 2, right? So the area under this curve is actually equal to 2. So this is a reasonable approximation that we got just by using 4 rectangles. Again, we can make this approximation better by letting the number of rectangles go to infinity. So like 8 rectangles, for example, would give us a much better approximation. Okay, what about the midpoint approximation using 4 rectangles? Well, again, the midpoint approximation, it's delta x, and then the sum starting at 1, stopping at 4, and then f of a plus I delta x minus delta x over 2. So again, the function is just the sine function. A is 0, so we don't write that down. And then plus I times pi over 4. So there's the I times delta x part, and then minus delta x over 2. So pi over 4 divided by 2 is pi over 8. So here's the thing we need to work out. So I'll write down the pi over 4. When I is equal to 1, I get pi over 4 minus pi over 8. That's just pi over 8. When I is equal to 2, I get pi over 2 minus pi over 8. That's going to be 3 pi over 8. When I is equal to 3, I get 3 pi over 4 minus pi over 8, 5 pi over 8. And then when I is equal to 4, I'm going to get 7 pi over 8. And so again, you can run this through a calculator and you get 2.0523. Note that this midpoint approximation, once again, is actually closer to the area, which is 2, than the right endpoint approximation. And the same will be true for the left endpoint approximation. So generally speaking, the midpoint approximation is the best one. Okay, let's look at one more example. Okay, so here's an example where we sort of have to do this process in reverse. So here we're given a sum, and we're told that this thing approximates some function y equals f of x on it approximates the area under y equals f of x on the interval from a to b, and we're using n rectangles to do that. So what's the function and what's the interval going to be, right? What is it that this thing is approximating? Well, it looks like since we go from 0 to n minus 1, let's try the left endpoint approximation. So let's say the sum from I equals 0 to n minus 1 suggests that we've got the left endpoint approximation, because remember, the left endpoint approximation starts at 0 and stops at n minus 1. So remember what that is. That's delta x, and then the sum I goes from 0 to n minus 1, and then f of a plus I times delta x. So we just need to figure out what f is, and we need to figure out what the interval from a to b is. And we've got a pretty good indication based on what's going on here. So in the next slide, let's compare all of the parts in this sum with the things in this sum. All right, so here's the sum that we're given, and we know it looks a lot like the left endpoint approximation, which is given by this thing. So just by comparison, we can sort of see that delta x is going to be 5 over n. And if I let f of x be e to the x, then I can see that f of a plus I delta x, or f of negative 2 plus 5i over n, is going to be the summand in the top here. So I'm going to get e to the negative 2 plus 5i over n. So it looks like the function in this case is going to be e to the x. And now if delta x is 5 over n, if you see here, then I've got a should be negative 2, delta x is 5 over n, and then we're just multiplying by I. So it looks like delta x is 5 over n. I know that's given by b minus a over n. It looks like a is negative 2, and so I know that 5 over n is going to be b plus 2 over n. And so the n's cancel, and that tells me that b should be equal to 3. So the final answer here, the function is just e to the x, and the interval goes from negative 2 to 3.